Okay, so today we will first finish two exercise problems in this chapter 3, part 3 on this circular orbits and stability. Okay, so you can pause the video here for a moment. Okay, so to try to look at this exercise problem. So in this exercise problem, what we have is a mass spring system. Okay, so one end of the one end of the spring is attached to a mass block, right? So, and the other end is fixed at the origin. Okay, and here you can see that I have this mass going along a circular orbit like this. Okay, so this is the initial condition that we set. Okay, and in this exercise problem, okay, so we want to show that the circular orbit of this mass is a stable circular orbit. And then we want to find out the frequency of the small oscillation, right? So that is to say, after you have set up the circular orbit, and suppose at some moment you try to give a little kick to this mass block, right, such that it displays a little bit away from the circular orbit, right? So if it does perform the oscillation, right, so maybe the trajectory of the mass will be something like this. So again, right, so if we want to find out whether it's stable or not, we need to consider the effective potential. Okay. So effective potential, remember that it is composed of two terms, right? So the first term is the centrifugal term. And the second term is the actual potential, okay, so due to the central force, right? So in this case, the central force is given by the spring, right? So, and that's why the potential energy is 1/2 k r squared. Okay, so r is the distance between the fixed point and the mass. And here you can see that I make an assumption is that the natural length of the spring is 0, right? So that's why the extension of the spring is r itself, right? So if the natural length of the spring is non-zero, suppose if the natural length of the spring is h, then the potential term that you write down should be 1/2 k r minus h squared, right? So, but I make this assumption, this 0 assumption is just to make the math easier. So what's the next step, right? So the next step, of course, is to take the derivatives. So this u prime is given by this one. So for stable, well, for circular orbits, first of all, right? So is that we want to have the point where u prime is 0. Right, so that is, I assume that the radius of the circular orbit is r0, right? So that is u prime at r0 is equals to 0. Right. So that is this. So that the circular orbit has this radius R0, which is given by this expression here. So now I want to find out, right? So the second order derivatives. And clearly, this second order derivative, you look at the two terms added together, must be a positive number, right? So it doesn't matter what R is, because you do have the first term, right? So only the square term and the power 4 term, right? So it must be a positive number, and then the k itself is also a positive number. So that's why the second order derivatives are always positive. And if I want to find the second order derivative at R0, right? So I just do this. And if you actually substitute this value of R0 over here, you'll be able to see that the first term is actually just 3k. And the second term is right k. So then we have 4k in total. So what does it look like if we actually plot the U effective? Right, so the first term looks like this. And the second term looks like this. Right, so if you sum them up, then you get a curve that looks something like this. Right, so here you can clearly see that this is the stationary point, and which is a minimum point. So finally, we want to find out the frequency of oscillation. Right, so then what you have is just this one. And this is square root of 4k divided by m. So 2 times square root of k divided by m. So that's the answer. So you might find it a bit interesting, right? So if you just consider the spring, the mass spring system in 1 dimension, if we're just doing this one dimension oscillation, right? So you know that the frequency is square root k divided by m, right? So but here, the frequency of this small oscillation when it is doing this circular motion already is 2 times square root of k divided by m. Okay. And this is different compared to the square root k divided by m is because now the oscillation, the force that make the oscillation happens. So basically it is a combined effect of the 2 terms, that is the centrifugal terms and the real potential terms, right? So that's why it is not surprising that this is different from just square root k divided by m. So then the next exercise problem is quite different from all the other central force problem that we have considered so far. Okay, so because what we have so far is really the force is pointing to one point, right? So, and then the orbit, the motion of the particle is just lying on a 2D plane. So in this problem, the setup we have is that we have this whole system, okay, just under a uniform gravitational field, okay, just mg, just always pointing down. And as shown in the picture, so you can see there's a cone. There's a cone surface actually, and then what we have is a particle touching the inner surface of the cone. Okay, so and it is free to slide. Okay, so everywhere along the cone's inner surface. So now what we want to study is the following, right? So suppose you give some appropriate initial condition, okay, so such that the particle is moving along a circular orbit, right? So just like the one that's shown by the dashed line, okay, by the dashed line, like this one. And then now let me draw a cross section of the system. If I draw the cross section of the system, looks like this. Right, so you could then imagine that this particle over here is moving into the page, right? So now I want to study whether this circular orbit is stable, right? And you'll see that indeed it is. So and next, what we are going to do again is to give a small perturbation of for the particle, is that you try to give it a small kick, okay, so such that it slide up a little bit along the cone surface, right? So just like over here. So if it does the small oscillation, right? So that means that this particle will go up, down a bit, and then up again. Maybe something like this, right? So if you look at the cross section, right? So this green particle is doing some up and down oscillation like this. Okay, so how do we approach this problem? Okay, so because this is, I said this is not quite the same as the central force problem that we have been considering. It's because now in reality, this is really a three-dimensional a problem, right? So, and the gravitational field gravitational force is pointing downward, instead of just pointing to one point, right? So, but it is because of the fact that gravitational force is not the only force in this problem, right? So we also have another force, which is the normal reaction force. So the other force that we have is this normal reaction force indicated by this blue arrow, right? And this is the one that make the whole problem, okay, effectively as a central force problem. So now, if we go ahead and use our usual strategy, what would that be, right? So that is to say that we would the usual strategy that we take is that we are going to consider the so-called effective potential, right? That is, if we are able to write the total energy of the system as this form, right? So then we can just take the effective potential to and do the derivative, and then we are done. So, however, the question is whether the total energy of the particle in this system over here can be written as something like the form, okay, so in the red color. So okay, I have to remind you that this problem is actually taken from your textbook, and you can also refer to that, but the approach we are taking here is a bit different from the one shown in the textbook. Okay, so if we actually go ahead to write down the kinetic energy and the potential energy of this particle, so what do we have? Right, so because in here, we don't have just R and the theta variable, because it really is a three-dimensional motion, right? So as you can see in the graph, the variables, the coordinate variables that we are going to use is the R, theta, and Z, right? So that's the convenient choice for us, right? So just to use the cylindrical coordinate. Right, so therefore, if we actually write down the kinetic energy of the system, right, so that would be 1/2 mv squared. But the V has three components. Okay. So, but one thing is the constraint, right? So because of the particle is always moving along the surface of the cone, right? So we do have one constraint that can eliminate one coordinate variable, right? So again, if you look at this cross-section picture over here, right? So this distance is R, this vertical distance is Z, right? So that is for the particle, R divided by Z is given by tangent alpha, right? Or Z is given by R divided by tangent alpha. So this is the constraint equation that we'll use, right? So, and right, so this Z dot can be written as R dot square divided by tangent square alpha. Okay, so then that's why the whole thing for the kinetic energy can be written as this. And in fact, right, so this one can be just written as 1 divided by sine square alpha. So, and as for the potential energy, it's just mgz, right? And I can again write it as mg times r divided by tangent alpha. So now you can see that the total energy of this system, right, so indeed can be written as a function of two variables only, right, so r and theta. So, but the question is, can we actually really write it as the form that is the same as the form of the red words, of the red letters, right? So because here I don't just have mr dot square, I have this mr dot square divided by sine square alpha. So now one more equation that we'll use. Let me just first also write it here. Is that L is equals to mr square theta dot. Okay, conservation of angular momentum. So if we also plug this L equals mr square theta dot into the KE term, right? So then I'll just open a new slide to again write down the expression for the total energy, right? So the total energy, right? So this is KE plus PE can be written like this. Right, so this is the energy. So, but the form that we hope to get is what? It's like this. So then as I said, it seems that we have the problem that we have here is this factor, right? So the sine square alpha. So next, what I'm going to do is to define a new thing called the capital M, right? So I call this, define this capital M to be M divided by sine square alpha, which is this term over here. So then the first term, I will be able to just write it as 1/2 mr dot square, right? 1/2 capital M r dot square. And I also want to express the second and the third term in terms of capital M. So if I actually do that, then it would be the following. Okay. So now if you compare the green expression, the form of the green expression, right? So with this form, right? So then now we can call the second and the third term as the U effective. So I'm going to call this the U effective. So, but so one thing is that the first term of the U effective is not just L squared divided by 2mR squared, right? It's this L divided by sine alpha all square divided by 2mR squared. But that's okay. So I'm going to again define a new thing called L prime. So, and as you might guess, right? So the L prime is defined as L divided by sine alpha, right? So then the U effective I have is L prime squared divided by 2 capital M R squared plus capital M GR sine alpha cosine alpha. So now I'm able to express the total energy of this system, okay, to have the same form as this one that we had in the central force problem. Okay. So then I just need to work on the U effective now, right? So if I go to take the first order derivatives, right, so then what I have is right. So and I want to, so if I want to find the radius of the circular orbit, right? So I'm looking for the zero of this U prime R, right? So and now I assume that the radius of the circular orbit is U naught R naught. Then right, so this whole thing is 0. So from here you can obtain R naught, right? So you could have this R naught to be equals to and this is R naught, okay, in terms of the other variables, the other quantities. So now if I going to take the second order derivatives, okay, so what do I have? Okay. So is that the U effective double prime is the following. So and clearly this is always this is positive, right? So and now well, if you want, you can also substitute value R naught over here. So that then we show that we do have this stable circular orbit, right? So and now if I'm going to find out the frequency of the oscillation, right? So this is the same formula that I just need to use. Right, so now because I express the whole thing in terms of this capital M, right? So then this is the U effective double prime divided by big M. Okay, so not small m. And this can be expressed as okay. And in the end, let me just express the final answer in terms of the real mass of the system, right? So the small m, and that would be this. Okay. So although we have finished the problem, so I would like to have a second look at this problem. Okay, just I want to kind of also treat it as a review exercise. Okay, so for the last chapter on the Lagrangian mechanics. Okay, so here I simply want to find the equation of motion for this particle in general. Okay, so I'm not thinking of the small oscillation in particular again. Okay, so I just want to go back to practice one more time. Right, so the Lagrangian formulation for this system. Right, so the Lagrangian of this particle, of course, is something that we don't need to work out again because we already find the potential energy, right? So the and the kinetic energy, right? So the total energy is over here already, right? So I just need to put a minus sign here in order to get the Lagrangian, right? So therefore, let me just directly write down the Lagrangian over here. Right, so but okay, I should also mention that when I write down the Lagrangian, okay, I should not have the L square here yet, so I want to write it down in both coordinate, right? So r and theta. Okay, so the Lagrangian I have is the following. So this is the Lagrangian, right? So and if you go ahead and use the Lagrange equation, right? So Lagrange, we will have two Lagrange equations, one for r, one for theta. Right, so the partial L, partial r minus ddt partial L, partial r dot equals 0. And that would give me this equation of motion. Okay. So, and the other one? And that would give me, right, so the change in angular momentum over time is 0. And that means I can define this mr squared theta dot, right, so it's the L. So that's the equation of motion, right? So, and now if you want to actually consider the circular orbit only, right? So you can also do that, right? So by considering the equation of motion we just obtained, right? So if you want to consider circular orbit, right? So that means that R of t is constant, right? So therefore, that is to say, R double dot, of course, is 0. Right? And that, right? So from the first equation, that would give me R theta dot square equals G cosine alpha divided by sine alpha. And this R theta dot square can be written as L square divided by M square R cube. So, and this, if you look at this relation, right, so that would be equivalent to this relation here, right? So because here we will be able to find out the radius for the circular orbit, right? So that's why this relation must be the same as this one. So and lastly, right? So if you want to do the Newtonian way, right? So then what you need to do, right? Just consider the force. Right, so this is the particle, this mg, this is the normal reaction n, and this angle is also alpha. So if it's doing circular motion, okay, so then the vertical, right, so the vertical component of n, which is n sine alpha, has to be equals to the gravitational force mg, right, so that it doesn't move up or move down. And then the horizontal component of the normal reaction n cosine alpha has to give me the centripetal force. Okay. So if you divide the two equations, you should have the same relation as this one over here. Okay, so this is the end of the chapter 3, part 3.